Okay, so welcome to the first day of linear algebra. Um, Today I'm just going to go over some background for the course, tell you about some of the kind of the main players that we'll see, and then I won't do anything too detaily, just give some examples and then hopefully give a flavor of what this, what we'll study in this class. Okay? So one of the basic objects that we're going to study in this course is a vector space. Okay? So let me just start with kind of a motivating example. Okay? So this is going to be R2. So the xy plane. Okay, so pairs of real numbers, ordered pairs. Okay. So I'll just draw the picture here so we can get some geometric feeling for what's going on. Okay, so what can we do here? What can we do with pairs of real numbers? Well, a simple thing that we can do is that we can add them together. Okay. So we can take x1, y1 plus x2, y2 and declare that this is just going to be x1 plus x2, y1 plus y2. Okay? So in other words, we have a plus operation on the real numbers, right? We know how to add here. So we can just extend this to R2 coordinate-wise. So you add the first coordinate and then you add the second coordinate. Okay? So geometrically you're taking, this is I guess called the head to tail picture. So I'm drawing it with arrows, though really this is just visual aid. Okay, so we take x1, y1, take x2, y2, and then the way that you see what the added vector is you take the head of one and add it to the tail of the other. Doesn't matter which order you do this. So you get x1 plus y1, x2 plus y2. Okay? So this, satisfies basically every property that you would think. Okay, so it satisfies the typical properties of plus. So maybe I'm not going to write down in details what they are. You can kind of see on the first page of the textbook. Okay, but it's associative, commutative. There's a zero. Okay, existence of zero. There's an existence of inverses. Okay, so maybe just, if you want to think about this, let's say pause and think, what is zero? So in other words, what is the pair, x, y, so that when you add that to any other value, it stays the same. Okay, so what does 0 mean? Okay, and what is, the inverse of x1, y1. Okay, so in other words, if I take a vector x1, y1, what do I add to it to get 0? Okay. Okay, so that's one thing we can do if we have pairs of real numbers. We can add them just coordinate by coordinate. Okay. Another thing we can do is that we can multiply by real numbers. Okay. So in other words, we can take, we'll call this for alpha in R, we can take a pair of real numbers, x, y, and say that we can multiply this by alpha, and the way that we do this is just multiply each one by each x and each y by alpha. Okay, so geometrically, what this does is you take a coordinate pair x, y, alpha, well, I'll draw the arrow again, and what alpha does is it multiplies, I guess I'm drawing alpha bigger than 1, so I get alpha x, alpha y. Okay, I guess I could have, if alpha was less than 1, I'd see it here. I can also multiply by negative numbers, so I might get something like this. So in any case, what I get is that this operation either expands vectors or expands the plane, shrinks the plane, or does this kind of flipping through the origin. Okay? And it satisfies, again, the usual properties, which you just get from multiplication of real numbers. Okay, so again, I'm not going to write everything out, but there's again an identity, okay, which is when you multiply by 1. It's associative. So it's important that it's distributive. Okay, so when I take two coordinate pairs and add them together and then multiply by alpha, it's the same as multiplying each of them by alpha and then adding them together. Okay. Anything that you might expect from multiplication in R is going to be kind of satisfied by this procedure. Okay? So let me put this here. We can do, let me just note, we can do the same for Rn. Okay, so this is just, instead of the Cartesian product of, or instead of looking at ordered pairs, we can look at ordered n-tuples. Define addition in exactly the same way, and multiplication in exactly the same way, just coordinate by coordinate. We can also do the same for Cn, okay? So this would just be, well, I probably should use a different letter, but that's okay. So this is just n tuples of numbers where everything is in the complex numbers, okay, rather than the reals. So maybe I'll just make a note here, is that if you haven't really seen the complex numbers too much, I wouldn't worry, or I wouldn't worry too much about the complex numbers, though, you know, if you're rusty on them, review them, okay? So just kind of keep that in your back of your mind, that you should kind of, at some point, we'll have to use facts about the complex numbers. But in this course, you know, most of the things we do don't depend on, you know, R or C, okay? So we'll see a little later what kind of the general story is, but if you just think of the real numbers for the majority of the course, well, for the majority of the course, you'll be okay. Okay, so maybe I'll just give a remark here, and something to think about. I'll pause for a little bit. So why can't we multiply coordinate pairs? So why can't we multiply x1, x1, y1, x2, y2 to be equal to x1 times x2, y1 times y2? So, you know, I said we can add these coordinate pairs, and of course we can also multiply coordinate y's too. Why is this kind of bad? So I'll say, why is this bad? Okay, and I'll pause here. Okay, well, so one answer is that, well, it's not actually, I mean, it's not completely terrible. We can do it, right? You can certainly do this operation. But notice that this has one bad property, okay? Which is that you might take x1, y1 times x2, y2. This might be 0. Okay, so the coordinate pair is 0, 0, even though each term is not 0. Okay, so you can multiply two coordinate pairs together and get 0, even though each one is non-zero. So for example, you can have 1, 0 times 0, 1. Okay, this is just 0. And this is kind of a bad property for multiplication to have, right? So notice this is not true if you want to think of multiplication of the real numbers, right? It's an important feature of multiplication in the reals that if you multiply two non-zero real numbers together, you get a non-zero real number. Okay, and this wouldn't happen here. So, it's not saying that you can't do something like this, but it ends up being less useful because of this property. Okay, so this is kind of going to motivate now the definition of a vector space, which I won't give precisely, but is in the book. Okay. It's also, I think I said vector earlier. It's very hard not to think of R2 and not call them vectors. Okay. So what is this? This is a set of vectors, which I'll usually denote the elements will be denoted by V, W, U, and so on. Okay, so letters. Okay. There's an addition operation. So you should think a vector, so the set here is an ordered pair, or an ordered n-tuple of real numbers or complex numbers. This is what we've seen so far. Okay. So what we can do is add them. So there's an addition operation, V plus W, and there's what's called scalar multiplication, which means that we can take a vector and multiply it by a number where this alpha is either, so alpha is going to be, for us, is really going to be in the real numbers or the complex numbers, okay? And really what I should say here is, I should either say that this is an R vector space or a C vector space. In general, this alpha, so maybe I'll just say this, in general, alpha is in a field F, okay? So we won't be using this generality very much. We're mainly going to be doing real numbers or complex numbers, okay? But I will note, so I will use the notation F whenever, a result does not depend on R or C, okay? Does not depend on what field you take. Okay, so if I prove something, it ends up being true no matter, if you choose the real numbers or the complex numbers, then I'll just say, I'll just use the notation F. Okay, and it will essentially be true for all fields. So let me give you two examples of other fields, right, that you might be interested in. So we could take, only look at multiplying by rational numbers. That's perfectly fine. Okay, so for example, I could look at n tuples, of rational numbers. This is a rational vector space, okay? It's not a real vector space because you can't multiply this by real numbers and kind of stay in the rationals, okay? You could another, great field is just the field on two elements. So this is just 0 and 1. I should specify the addition and multiplication. It's just addition and multiplication mod 2. Okay, so 1 plus 1 is 0. 1 times 1 is 1. Okay? So again, you could think of ordered pairs, f2 to the n. X1 through xn, xi, and f2. So this is just, strings of length n, so we'll say n strings of zeros and ones. Okay, so n binary strings. I don't know what the right words are. Okay, so we have, at this point, 4 examples, but they're all very similar examples of vector spaces. So we can take Rn, Cn, Qn, f2 to the n, addition, and scalar multiplication are defined coordinate-wise. Okay, for all the examples. Okay, so what I would like to do now is actually give you more examples of vector spaces. Okay, so ones that don't look at first glance like any of these examples. Okay, so maybe at this point it would be a good idea is go to page 1 of the book. Okay, which will have all of the axioms for a vector space that we'll be using, okay, which I haven't written down. Okay, and then when I give you these examples, now you can kind of verify in your head that they're going to satisfy the axioms. Okay, so let's see some other examples of vector spaces. All right, so just to have the idea, this is quite a general definition, right? I've essentially said you have a set, I know how to add things in this set, and I know how to multiply by some, let's just say, real or complex number. Okay, so that's pretty general, and we'll see that you get other things rather than just Rn. Okay, so here's a nice example, which is the space Pn. So this is polynomials of degree at most n. Okay, so in other words, this looks like f of t, so it's going to be a0 plus a1 t plus a2t squared all the way to an t to the n, okay, where the t is just a variable and the a sub I, well, are going to be in whatever field you want, okay? So these could be real numbers, they could be complex numbers. And now this is a vector space over f. Okay? And so what do? So I have to tell you how to add, right? And how you multiply. Well, addition is just addition of polynomials. Okay? And multiplication, so scalar multiplication, is just multiplying the AIs by the scalar. Okay, so multiplying the polynomial by scalar. Okay, so each term gets multiplied by alpha. Okay, so maybe I will, again, you don't have to check all the axioms, but you should think about, why this should work. Okay, and maybe I'll just pose as a question, which I'll pause and then give the answer. Okay, so why is, let me call it Rn, so to be the polynomials of degree equal to n, not a vector space. Okay? So notice here I said at most n, so I had polynomials up to n, but I could have taken just a polynomial, 1 plus t, right, or 1. So why, if I make it have to be equal to n, why do I not get a vector space here with the same addition and multiplication? Okay, so I'm going to pause here. Okay, so the answer is that, well, you can add two polynomials of degree n and get a polynomial of degree less than n. Okay, so for example, 1 plus t and 1 minus t. Okay, so of course this is something to be careful of when you're defining, your multiplication. And in addition, that you need to stay within the set for both of them to be well defined. Okay, so kind of a similar problem or phenomenon. Okay. Oh God, can't spell that on the fly. So we also know that we can multiply polynomials together. Right, we know how to do this. In the same way, the degree goes up. Okay, so but the degree goes up, right? You take a degree n polynomial and a degree m polynomial, get an n plus m polynomial. So you can't define a multiplication on this set Pn. Okay, maybe I'll just mention that if you take P to be the union of the Pn, so in other words, P is all polynomials, okay, then P is a vector space still. Okay, you define the exact same addition and scalar multiplication, but even better, you can now multiply. Okay, so this just means that, if you take the union of them, you now have additional structure, okay? Additional algebraic structure, which you aren't guaranteed with for just a vector space, all right? So maybe we'll see at some point when when you're allowed to multiply vectors and what this extra structure kind of gives you. Okay? Okay, so let me give you some more, I just want to do more examples now. Okay, so that's a very nice example, an important space of polynomials. Another one is more general. Okay, we can take V to be any vector space. Okay, just again this set with these operations. X is going to be any set, and we make a new vector space. Which is going to be, I'll denote it by V to the X. So it consists as a set of just functions from the set that you have to the vector space. Okay? So you can think, for example, if X is 2 points and V is just R. Oh, so maybe I should say I didn't need, when I was taking R to the N, R is a perfectly good vector space over itself, right? You can multiply, you can add. Okay? So then the reason, if I set up my notation correctly, if I look at functions from a 2-point set to R, so V to the X, this is really just R2, okay, XY. Because functions from a 2-point set to R is the same thing as ordered pairs of real numbers. Okay, but you can do this in general for any set X. And define addition, well, you know what to do now, right? How do you define, if I take F and G, two functions, well, the way that you add two functions is you know how to add f of x and g of x since these are vectors. Okay, so the way that you define f plus g of x is just f of x plus g of x. So these are both in V. So I know how to add them together. Similarly, the scalar multiplication, if I want to define an alpha f of x, well, again, f of x is in V, so I know how to scalar multiply there. So I just get alpha f of x. Okay, so really I should say this is alpha f, and then what it assigns to f is just alpha f of x. Okay, so maybe I'll give this as a question, okay, and then again I'll pause and then an answer. Okay, so in any vector space, kind of as an axiom, we have a special zero vector. Okay, so this is just part of what we're given. Okay, so if I want to check that, I've checked kind of that we have these operations, but for this last example, we have addition, we have scalar multiplication. Okay, but what is 0 here? Okay, so what is the 0 function? And also, I'll say, what is the inverse? Okay, of f from x to v. Okay, again, this is additive inverse. Okay, so I'm going to pause here and then answer. Okay, so for the answer, we have to figure out what function from x to v, if you add it to any other function, it is the same. Okay, so here, the notion of 0 is the function f from x to v, which sends any element to 0. Okay, so it's the 0 function. All right, so notice when you plug, if f was the 0 function here, then since you have a 0 here, then g of x would just stay the same. Okay, so f plus g of x is just g of x. In the same spirit, the inverse function, so negative f from x to v, just takes any element x and sends it to negative f of x. Okay, so again, I know how to, this is an element of v, I know that there's an additive inverse here, so I can just send the element x to there. Okay, and you can check that f plus minus f is going to be the zero function. Okay? All right, so let me continue with some more examples. All right, so the next one is going to use some properties of derivatives as a natural place where linear algebra comes up. I'm not assuming we know what a derivative of a function is yet, but it's useful for this example. Okay, so let's take as a set. Sorry, so this is my set. It's going to be functions from R to R, which satisfy the equation f is equal to its derivative. Okay? So this is my set. Addition and scalar multiplication are going to be exactly the same, or exactly the same as you would think. Okay, so addition is addition of functions. Same with scalar multiplication. Okay, so we can multiply a function by alpha and r. Okay, and notice that when we add two functions from here, or when we multiply by a function, it will still satisfy this condition of equaling its derivative, right? So if I take, for example, the derivative of f plus g, okay, this is just equal to the derivative of f plus the derivative of g. Okay, so if f was equal to its derivative and g was equal to its derivative, then the derivative of f plus g is equal to is the same as f plus g. Okay, so this equation is still satisfied. Same thing if I take the derivative of alpha f of x. This is just alpha times the derivative of f. So if if f is equal to its derivative and I multiply by a real number, this will still satisfy this this property. Okay? So in fact, the key thing here is that the derivative is a linear transformation. All right, so what I mean is that it satisfies these two properties. Okay, that if you take the sum of two functions and you take its derivative, it's the same as taking the derivative of each factor and adding them. Or if I take a function, multiply it by a number, it's the same as take its derivative, then it's the same as taking the derivative and then multiplying by a number. Okay, so the same thing would have worked. So this works more generally. Okay, so for example, I think here we kind of know what the set of functions would be, but actually you can look at any linear differential equation and it will the same thing will work. It will be a vector space over the real numbers. Okay, so for example, if I take functions which satisfy second derivative plus the first derivative plus the function is 0, okay, then the solutions by the same argument are going to be a vector space over the real numbers. Okay? So I'm going to give, I guess, 3 more examples, and then I think I'll probably just end for the day. Okay? Again, you should think kind of for all of these, what is the 0 vector space, or what is the 0 element, and what is the additive inverse? Okay? So here's another example. So I can take functions from n to r. Okay, so this is just, sequences of real numbers. Okay, so I can take functions from n to r satisfying this equation where this relation where f of xn is equal to f of xn minus 1 plus f of xn minus 2. So in other words, this is the set of Fibonacci sequences where the first two values are completely arbitrary. First two are arbitrary. Okay, so a sequence might be, you could have the usual Fibonacci sequence, or you could take 1, minus 1, 0, minus 1, minus 1, minus 2, and so on. Okay? That's your set, okay? And you can check that it's well defined to have addition. It's just addition of sequences. And multiplication, scalar multiplication is just, multiply each term by a real number. Okay? And so the important thing to check is that, what happens is that if you take this relation and you add two sequences which satisfy this relation, you'll get a sequence which satisfies this relation. So adding two Fibonacci sequences gives you a Fibonacci sequence. Multiplying a Fibonacci sequence by a real number for every term spits out another Fibonacci sequence. Okay. Oh, so I think I should have said here n is greater than or equal to 3. All right, for the first two are arbitrary. Okay, so that's another vector space. Okay, so here's another one. This is either too many examples or still not enough examples. Okay, so here we're going to take the set is going to be the positive real numbers. And it turns out this is a vector space over the real numbers. Okay, so I think this is kind of surprising, right? Because you think when you're defining a vector space, well, you should have, there's no 0. You should have, if you're multiplying by negative real numbers, you should have to include the negative real numbers in your set. Okay? But the point is that the addition and multiplication are going to be quite different. Okay? So here, my, addition is going to be, I take two vectors u and v, so two positive real numbers. U plus v is going to be the product, uv. Okay? So the way that you add in this case is you multiply the two positive real numbers together. Then how do you scalar multiply? So scalar multiply. So I'm taking alpha u. Okay, so I define if I take a positive real number and I multiply it by, the way that I multiply by a real number is I take u to the alpha. Okay? So I exponentiate my term and raise it to that power. Okay? So, of course, this is, again, these are both, positive real numbers, since u and v are in the positive reals. Okay? And you can check, basically that the rules of exponents, laws of exponents, guarantee, the axioms that we require from addition and scalar multiplication. Okay? So again, here's, what I would check here is, so what is, I won't do this, I'll just leave it for you. What is the 0 vector here? And what is the additive inverse? Okay, it's also a good idea to check just the axioms in this case, since it requires a little more than anything we've seen before. Okay, so let me give one last example, just because I do like the field with two elements, so I want to give you an idea of just like what a F2 vector space might look like. Okay, so again, remember what we're allowed to do here is, well, we're allowed to take we're allowed to take a set, you have to add it, and then you have to be able to multiply by just an element of F2. Okay, so here is an example, okay, which you can, real world example. Okay, so take your house, look at all the light switches. In there, and look at all possible settings. Okay, so I'm assuming you don't have dimmer switches, so it's just on and off. Okay, so you might have, 10 lights in your house, 10 different light switches, and they can be in various settings. You could have this one being on, this one being off, and so on. Okay? So you get something like 2 to the 10th possibilities here. Okay, so 2 to the number of light switches, that's the cardinality. Okay, and then what do you do? Okay, so how do you, how do you multiply? I'll do the multiplication first. How do you do scalar multiplication? So you have to multiply by an element of F2. Well, 0 just does nothing. Okay, so remember the F2 is just 0 and 1. 0 doesn't do anything, and 1 flips all the switches. Okay, so you can be the element of F2 yourself by going around your house or apartment and then just going to every light switch, and if it's on, flip it off, if it's off, flip it on. Okay? So that's how you scalar multiply, and then addition. So if you have two different settings, you just say, well, off plus off is off. Off plus on is on. And on plus on is off. Okay, so you can imagine it. I mean, if you flip something on and then you flip it on again, so if you've done a flip and then flipped it again, you've flipped the light switch off. Okay, and you can check that this is, again, a vector space over F2, satisfies the usual axioms. Again, you can check, so I would check here what's 0 and what is the additive inverse. Okay, just to keep it straight in our heads. Okay, so hopefully you've seen enough examples to convince yourself that there's a lot of possible vector spaces out there. And so maybe I will stop here, and then in the next lecture start getting more into details of vector spaces, some operations that we can do to them, and some more explicit examples. So, okay, thanks. See ya.